Okay. So today we're going to start looking at forces in two dimensions or two directions, right, with forces applied at an angle, right? If I pull something upward at an angle, if I push something at an angle, okay, we're talking about things that have both x and y components, right? And what do we know about physics at an angle? We don't like it, right? We don't like it. We break things down if they're at an angle. We break them into their x component and their y component. So we're doing that with forces as well, okay? The good news is that we already know how to do this because we did it with projectiles, okay? We already know how to break these vectors into components, right? Using sine, cosine, tangent, using all those trig functions. We know how to do that. So this is just going to be kind of an extension of that vector addition type stuff, except now we're looking at it in terms of a free body diagram, okay? Okay, so what we want to do is find the sum of these two forces that are pulling the boat, okay? Do we see where there's the little guy here pulling the boat from up here on this shore? There's a guy pulling it from this shore. We can anticipate the boat's going to go somewhere in that direction, right? But what we have to do is break those forces into their x and y components, and we're going to end up finding our resultant force. Okay, it's just easy vector addition. That's all we're doing right now. Okay, this isn't even necessarily the free body diagrams that we're going to be looking at. This is just another practice with vector addition. Okay, so first thing that we need to do is break those forces down into x and y components. Okay, so let's make sure you got your calculators out. Make sure they are in degrees, not radians. Okay, make sure those calculators are in degrees. Okay, so I'm going to draw these two forces separately. Okay, my first force is 40 newtons at 45 degrees. So if I was going to label this side of my triangle, what do you think I would probably label it? Good, F1y. And this side would probably be called F1x. Okay. So let's go ahead and solve for that. Since it's a 45-degree angle, what do we know about F1x and F1y? They should be the same because it's a 45-degree angle. Are both of those components heading in the positive direction? Yes. Right? They're both heading in the positive direction. So what are my values for F1x and F1y? 28.3 and 28.3. Okay, and we found that by taking 40 times sine of 45 or 40 times cosine of 45. Okay, on the same page so far? Okay, let's look at our second force vector, which starts from our origin and goes downward. It's a 30 Newton force, and it's being applied at an angle 37 degrees south of east. So I'd call this F2x and F2y. So when I'm solving for x here, would I be using sine or cosine? Cosine. It is adjacent to that angle. Okay, cosine is adjacent, so I would take 30 times cosine of 37. Okay, what did we get for that value? Say it one more time. 24. Okay, and what about our y value? Negative 18. I'll round that to one decimal. Negative 18.1. Tell me why that value is negative. Going south, right? It's a south component. Going downward. So now we add all our x's and add all our y's to get the component of our resultant force. So the resultant in the x direction would be 28.3 plus 24. And the resultant in the y direction would be 28.3 plus negative 18.1. Do we agree with those resultant components? Yeah. Okay, so now we build our new triangle. Okay. So let's see here. If I were going to build my new triangle based on this origin, I would go 52.3 east, and then 10 in which direction? North, right? Because it's a positive. So 10.2, 52.3. So my boat ends up about right here. Okay? So I need to find my hypotenuse and my angle there to look at my resultant vector. All right, so what was the magnitude of my resultant vector? What was the hypotenuse? 53 point what? Okay. I'll round it up. At what angle? 11.3 degrees north of east. Do we agree there? Okay, so just write down what you need to from this problem. You don't need to copy it word for word, right? A force of 2,000 newtons acts at an angle of 60 degrees with respect to the horizontal. That just means, yeah, it just means it touches the horizontal, so it's north of east, okay? Is exerted on a towed car. Car accelerated from rest, 10 meters per second. Find the mass of the car. Let's look at what the free body diagram here looks like. Okay, so I've got my car. Gravity is always acting, right? The normal force is acting because my car's got to be sitting on something. And it tells me I've got an applied force that's going up at an angle, right? From the horizontal. So can we envision that towed car, right? A car's being towed, it's usually pulled by a rope that's higher, right? So that's that 60-degree angle. Okay? And it says our applied force is 2,000 newtons. Okay, so let's take a look at what our overall goal is here. It doesn't mention anything about friction. Okay? And it's not moving at constant velocity. So if it doesn't say anything about friction, we don't worry about it. Okay? So here, it says it's accelerating at a rate of 10 meters per second squared. Do you think that's probably vertical acceleration or horizontal acceleration? Horizontal acceleration. So that means are we concerned with the vertical forces or the horizontal forces? The horizontal forces, that's it. We don't really care about the vertical forces. Okay? Because we have no acceleration in the vertical direction. We don't really care about them at this point. So that means all we need to solve for is the applied x component. We don't even have to solve for y. Okay, so to solve for f applied x, we would take the hypotenuse times sine or cosine? Cosine of 60. And that's equal to 1,000 newtons, right? Oops. So if that means our only horizontal force in the x direction is equal to 1,000 newtons, doesn't that mean that our net force is equal to F applied x? Is there any leftward forces? No. So you can put in the -0, you can leave it off if you want. Okay, but when we set up our net force equation, we have to understand that it's always rightward forces minus leftward. And after we break down this angle, we do not use that force again, right? We only use the components. Just like when we broke down our initial velocity vectors, we only use the components after that. It's the same thing for these force vectors. So I broke that down into my x component. I don't have any leftward forces, so that's going to be 0. All right. What do I substitute in here for F net? M times A is equal to our F applied X, which is 1,000 newtons. Okay, do we see how we got there? F net can always be substituted for mass times acceleration because we know that Newton's second law tells us F net is equal to mass times acceleration. Okay, our applied force was X. We know our acceleration was 10. And so that means to solve for our mass, we're going to divide that over and we're going to get our mass equal to 100 kilograms, which is not a realistic mass for a car. Okay. Okay. Okay, a 50 kilogram washing machine is being lifted upward with a force of 200 newtons at an angle of 40 degrees. So it's not lifting purely upward, they're pulling at it from an upward angle. Okay, 40 degrees. The machine begins to slide. That's an important word there. Begins to slide. Find the normal force acting on the washing machine. So why don't you go ahead and start trying to put together your free body diagram. Okay. Do we agree with that free body diagram? Okay, so if I wanted to label this side of my diagram, what would I call it? F applied Y and F applied X. Okay, so now let's start thinking about this in terms of what forces do we need to solve for. Okay, it tells us that the machine begins to slide. So does that tell us it's accelerating vertically or it's accelerating horizontally? If something just, okay, so can we imagine what's going on here? I've got my little rope, I'm trying to pull my washing machine, I'm pulling at an angle, but it just starts to slide this way. Is it moving vertically at all? No, it's not moving vertically. We have no vertical acceleration here. It just is moving horizontally. Okay? But as I'm pulling that upward, it's taking some of the pressure off the normal force. So it's going to change our normal force value. Okay? So let's see why that's the case. If we know that it's not accelerating vertically, let's start looking at our net force equation in the y direction. Okay? Because the normal force is a vertical force, right? So that's where our eyes need to start going here. Okay? Our net force in the y direction is going to be upward forces minus downward. You have to take into account all upward forces. So how many upward forces do we have? 2, right? We have the normal force plus F applied Y minus what downward force? Gravity, right? The gravitational force. We don't really care about F applied X at this point. Okay? But what do we know since our washer is not accelerating in the vertical direction? What do we know about the net force? The net force is 0 since it's not accelerating in the vertical direction. So that means normal plus applied Y minus gravity is equal to 0. So if we move the gravitational force to the other side, that tells us that the gravitational force is equal to the normal force plus force applied y. Okay, so these two forces combined equal the gravitational force. Okay, so this is telling us that upward forces equal downward forces since there's no vertical acceleration. Okay, are we kind of getting there? Seeing where we're going a little bit? So now we can start doing and start plugging in these numbers. What do we know about F sub g is always equal to what times what? Mass times gravity. Okay, our normal force is what we're solving for here, so we don't need to substitute that in at all. F applied y we can solve for by taking our hypotenuse times sine or cosine times sine of 40 degrees. Okay, and you don't have to write this all the way out with all the variables. I'm just showing you how we're getting through this process. Okay, so mass times gravity, 50 times 9.8 equals the normal force, plus 200 times sine of 40, which I got to be about 128.6. Yeah? Okay? We include the negative for the downward force right here. So since we subtract out the downward forces, we just include the negative in the subtraction. So we're not going to do minus negative 9.8 because that'd be double negatives. Does that make sense? Okay. All right. Now we take 50 times 9.8, and our final normal force, I got to be about 361. Yeah? You can start plugging in your numbers at this step right here if you want. That's fine. I just showed you kind of how we can get these things together. So we could have plugged our numbers in right here and said the normal force plus 128.6 minus 50 times 9.8, and then we could have just moved this whole term to the other side and made that equal to the normal force. It does not matter algebraically how you go about doing that or when you decide to plug your numbers in. I just wanted to show you that when our net force is 0, when it's not accelerating in the vertical direction, our upward forces total should equal our downward forces, and that's what happened here. Okay? So our normal force ended up being 361.4. So is that less than or equal to it would be if there was no other vertical force? Less than, right? Because 50 times 9.8 is equal to what? 490. So if there was no other vertical forces here, our normal force would have been 490. But since we're pulling upward with that rope, we're taking some of the pressure off of that normal force. Does that make sense? Can you visualize what's happening there? You're lifting it upward, so you're taking some of that pressure off of that. Okay, if we would have been pushing downward, our normal force would have increased, right? It would be having to work harder because it had to work against us and against gravity. Okay? Okay, let's try another one here. This diagram is in your textbook if you want to look at it a little bit closer, but I think hopefully you can see kind of what's going on here. Uh-huh. Mm-hmm. Or F, yeah, they've said F pull, but yeah, you could put F applied there. Uh-huh. All right, so this one tells us 2 boxes are connected by a cord. They're resting on a frictionless table. Okay, that's important, frictionless table. Boxes have masses of 12 and 10, a horizontal force of 40 newtons. Okay, your book calls it FP because it's a pull. You could put F applied. It doesn't make any difference. Is applied by a person to the 10 kilogram box. Find the acceleration of each box and the tension in the cord. All right, so let's start by looking at a free body diagram for each box. Okay, so here we've got the pulling force. And then going the other way, we've got that tension force. So I'm going to say F sub T. Let me get a different color here. That's kind of hard to see. tension force. And then we've got gravity and the normal force. Okay, do we really care about our vertical forces here? No, we're not accelerating vertically. There's nothing else going on here crazy. Doesn't mean we don't have to draw them, but we're not really concerned with what their value is at this point. Okay, this box, we've got gravity, normal force, and what other force is going on with this box? Right, yeah, this tension force because of that rope. Okay, and we don't know what the tension force is equal to yet because we're trying to solve for that, right? The tension of the cord and the acceleration of the boxes. So we're not sure what the tension force is equal to just yet, but we're going to be able to algebraically solve for those and set those equal to each other. It says, shouldn't these boxes have the same acceleration? Right? They're connected. It's kind of almost like they're one object at this point. So the box's acceleration should be equal. So I'm going to say acceleration of 1 is equal to acceleration of the box 2. Okay, because this box I'm going to call box 1. This box I'm going to call box 2. Okay, because we're going to have to label our subscripts a little bit more clearly here. So let's start by looking at the net force of the first box. Okay, so the net of the first box. We're going to take rightward forces minus leftward. So what would it be equal to? The pull force minus the tension force. And I'm just going to do it with just variables for right now, and then we'll go back and look at numbers. Okay? And then if I wanted to solve for F net of the box 2, what would that be equal to? Yeah, only the tension force, right? Because it's rightward, and we don't have any friction that's opposing that motion. Okay, are we on the same page so far?
Yes.
All right, what do we know about F net? What can we substitute here? So I can say mass of the second box times acceleration of the second box is equal to the tension force. Right? That's just a little substitution right there. Okay, now, since I have two systems of equations here, 1 and 2, can't I do a substitution? Right? For these variables? So I can say the net force of the first box is equal to the pull, minus mass times acceleration of the second box. Do we see algebraically how we got there? Okay. Doing some substitutions here, so you just have to kind of take a step back and look at what we can move and where we can manipulate our variables a little bit. Okay. From there, we know that both of our boxes will have the same acceleration, so we don't even really need to put the 2, but you are more than welcome to do that. Okay, that doesn't really make a difference. Now we can go ahead and start plugging in our numbers, right? Because we have some numbers that fit here. What do we know F net is equal to always? So now, since this is box 1, I'm going to say mass of the first box times acceleration is equal to the pull force. Oops, I keep writing it hard. Minus mass of the second box times acceleration of the second box. We already said that these accelerations would be equal to each other, so I'm going to get rid of those subscripts because we know it's just an A. That's what we're solving for. Okay, we know mass of the first box, right? Is 10. We know our pull force is equal to 40. We know mass of the second box. Okay, so now we can just finish our algebra problem and solve for A. Right? Combine our like terms, then divide that over. So I'm going to add 12A to the other side. And I got acceleration equal to 1.82. Sorry, that's kind of hard to see. 1.82 meters per second squared. Yeah? Yep. Okay. So now the last part is just taking that acceleration and plugging it into either equation to solve for the tension force. What would be probably the easier one to do it with? Yeah, right here, right? Mass times acceleration equals the tension force. So I would take 12 times 1.82 equals our tension force. Okay. So when we look at problems like this, we can assume that the mass of the cable itself is negligible. It's not going to give us enough of a difference to really be concerned with the mass of the cable. Okay, and most of the time it'll tell you that. In this problem it doesn't, but we don't really care about the mass of the cable. So let's look at basically this first section of rope right here. Okay, so if we look at basically the free body diagram beginning right here. Okay, so let's see, I'll change colors here so we can see it a little clearer. We've got a tension force going upward, right? And that's the tension of our first section of cord. We've got the gravitational force pulling it down. So in this particular problem, these tension forces within the cables are not the same because they represent two different portions. Okay? So the tension in this cable right here would not equal the tension in this bottom cable. Okay, they have two different kind of jobs here. So if we're looking at this first section, which is this top tension of our top cable, we see basically everything underneath of it is part of that mass. Okay, so we're concerned about the masses of both objects here. So when we set up our net force equation, upward minus downward, right, would tell us tension force minus the gravitational force. And when we're looking at this top section of cable, we need to understand that both of the masses hanging below it account for that mass, okay? Because if you think about it, everything hanging below that kind of just becomes one system now, okay? So that means when we start doing our substitutions, mass times acceleration equals the tension force minus mass times gravity, right? Do we see where those substitutions came from? F net equals ma, and Fg equals mg. So the mass now becomes 1,200 plus 7,000 times the acceleration, which is 2.10. But what do we know about this word right here? Negative. It's negative 2.10. Okay, because if something is being raised or lifted, we have a positive acceleration. If it's being lowered, we have a negative. We're solving for the tension force. And then we're going to plug that mass of the whole system in times 9.8. Okay, and again here this 9.8 stays positive because we take into account the negative right here when we subtract out those downward forces. So tension in the cable between these two. We're only concerned with the mass that's hanging under it. So this second time our equation would look exactly the same, except we're only dealing with the 7,000 kilogram object.